Okay. So coming to in wave optics, already we completed Young's double slit experiment and diffraction by a single slit. That is only there in the syllabus. Validity of ray optics, resolution of microscope or telescope, all that is deleted, and in complete polarization is deleted from the syllabus. Only intensity distribution pattern, difference between the intensity distribution pattern of interference and diffraction. These two are pending. But that's only it will take only 2-3 minutes to explain. The pattern I have to explain, that I will explain by the end of this lesson. So today I will start with this. Okay, what is that? Dual nature of matter and radiation. Very easy topic. Okay, these three lessons. I mean, dual nature of matter and radiation, atomic physics, and nuclear physics. You don't have any derivation. Hardly 1 or 2 derivations are there in each of the lesson. Okay. So you these 3 lessons you will enjoy. Okay. Now, I will start with the I mean the different processes. So I'll not erase this figure. I just drew it for you people. Okay, just I will use only this corner of the board so that it will be easy for me to explain. Einstein's photoelectric effect. Okay, this I'll explain. So I'll write here dual nature of matter and radiation. Dual nature of matter and radiation. Actually, this is the one where you can go from where the quantum mechanics started. From where the quantum mechanics started. You know what is quantum mechanics?
Yes, sir.
That's the study of
quantum
particles.
Study of micro and nanoparticles. Okay. So we study the behavior characteristic of micro and nanoparticles. Not other than electron, proton, neutron. There are so many particles. Around 105 particles are there. Around 105 particles are there in an atom. Maybe there, may not be there. Like ions, pions, mesons, baryons, kryptons, leptons, neutrino. Many are there. Again, there are subdivisions in each of the particles. So to study those particles, we have a new mechanics, quantum mechanics, where you cannot apply your normal mechanics. Where we cannot apply the normal Newton mechanics cannot be applied over in quantum mechanics. Again, okay, that we will see. Next one is we'll start with the particles first, the fundamental particles. Okay, so why the name was given as dual nature of matter and radiation? Because see, light has a dual nature. Light has dual nature. They say that one group of scientists they supported who like Newton, okay, Newton and Einstein, and Max Planck. They supported the particle nature of light. They said that light has a particle nature. Now, you know the next one, like Huygens, you know Huygens, who is Huygens? Christian Huygens and Young and all. There are some more scientists who supported the wave nature of light. They did it experimentally. It's not like just they told the theory. They experimentally proved it that light has a particle nature, and this group of scientists supported the particle nature. And this group of scientists, there are some more scientists, not only 3, maybe 5-6 scientists are there who supported particle nature of light, and there are 5-6 people who supported the wave nature of light also. Okay, so that is about that is about the particle. So we will, by the end of the topic, we will come to know what exactly light is. Is it particle nature or is it wave nature, and how it is so? Experiment, that also we have to prove experimentally. It's not like only theoretical base. Now, is it clear, all of you? Is this clear?
Yes, sir.
Yeah. So, sorry, it's my mistake. I should have asked you to join well time back. Okay, before. Now, anyways, so thank you for coming and joining the meeting. Now, see, there are fundamental particles. What are the? I'll start with fundamental particles because for these 3 lessons, I need again fundamental particles, all the 3 particles. So, what is an atom? Atom is a small. What is it? And the atom is an indivisible particle in the nature. Indivisible particle in the nature. Okay, atom is an indivisible particle in the nature. That already will. And then what are fundamental particles? What are fundamental particles? Can anyone say? Or basic building blocks of an atom? What are they? Yes, please.
Particles that cannot be further subdivided into smaller particles.
Yeah, that is good. What are they? They are electrons,
Electrons and quarks.
electrons, protons, and neutrons. Okay, they are
Okay.
electrons, protons, and neutrons. Okay. Okay, electron, proton, and neutron. So here we have. So first we'll start with electron. Electron was discovered by J.J. Thomson. Electron was discovered by J.J. Thomson, and charge of electron was discovered by R.A. Millikan by using liquid drop model. Okay. And what is the charge of electron? It is negative. Charge of electron is negative, which is equal to minus 1.602 into 10 to the power of minus 19 coulombs. And mass of the electron is 9.11 into 10 to the power of minus 31 kg. Okay, 9.11 times of 10 to the power of minus 31 kg. And if you are comparing the mass of electron to mass of hydrogen atom, mass of electron is 1837 times of mass of hydrogen atom or a proton. So this is the symbol E minus 1, 0 is the symbol. Minus 1 is the charge and 0 is the mass of an of an electron. Please do copy this one. Then we'll go ahead with the proton, neutron. Then we can start a specific charge of electron. Okay? Is that clear?
Yes, sir.
Do it fast.
Yes, sir.
Copy it. Okay, this you don't copy. This I have to explain because it will take time. So that's what I drew it before. This diagram. Okay, this is Einstein's photoelectric effect. Okay. Done, all of you? Is it done?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
1 minute.
Okay, yeah. Otherwise, okay. Okay.
Yes, sir. Done.
Okay. Okay, now, okay, I'll erase this part. I'll go with proton now. Okay. I'll just go with proton now. So can you tell me what the okay, who discovered proton? It was discovered by
Kelvin.
Rutherford.
Rutherford.
Okay. Proton was discovered by Rutherford and charge of proton was discovered by Goldstein. Charge of proton was discovered by Goldstein. Okay. Now, and what is the charge of electron? Charge is positive, and charge of proton is plus 1.602 into 10 to the power of minus 19 coulombs, and mass of proton is 1.66 times of 10 to the power of minus 27 kg, and the symbol is P1 and 1. One is the charge and one is the mass. Is that clear? Is it clear?
Yes, sir.
No. Copy this one, then quickly we'll go to neutron, then specific charge of electron. Please write a message in the group so for the student, for your classmates to join the class. Done with this?
Yes, sir.
Yeah. Okay, then shall I go with the neutron now? Yes.
Yes, sir.
Okay. Please be little louder. Okay. Not able to hear.
Okay, sir.
Okay. Now here we have neutron, the third particle, that is neutron. Neutron was discovered by Chadwick. Okay. Neutron was discovered by Chadwick. The charge of neutron is 0. Charge is 0. Don't say neutral. And mass of neutron is 1.67 times of 10 to the power of minus 27 kg. And if you are comparing the mass of neutron to mass of proton, mass of neutron is slightly greater than mass of proton. And that's it. So N01, we write 0 is the charge and 1 is the mass of the neutron. Here. Zero is the charge and 1 is the mass of the proton. Okay. Done. So I'll go with the specific charge of electron. This is specific charge of electron. It is equal to how much? E by m. We say E by m. 1.76 into 10 to the power of 11 coulomb per kg. This is an important value. Okay. It's a specific charge of electron or E by m ratio. Specific charge of electron or E by m ratio. Okay. Clear? So we'll go with the next electron emission, first case. Start with electron emission. Okay. Should I raise this now?
Yes, sir. Now here we will speak about, or discuss about that is 1 electron volt. What is 1 electron volt? The 1.602 into 10 to the power of minus 19
joules. Okay.
joules.
1.602 into 10 to the power of minus 19 joules. This is the value of 1 electron volt. Now, there are 3 ways in which electron emission takes place. Not many, there are many ways, but electron emission, he mentioned only 3 in your book. Okay, electron emission. How can we bring out the electron from an atom? Electron emission. So, in this, he discussed about 3 different cases. Number 1 is fermionic emission. Fermionic emission. First one is fermionic emission. Second one is field emission and photoelectric field emission and photoelectric emission. Field emission. The third one is photoelectric emission. Photoelectric emission. Okay. So we have 3 here. One is fermionic emission, one is field emission, the third one is photoelectric emission. These are the 3 different situations now. So we'll discuss one after the other.
Now what happens is, in this first emission, like suppose the first one. In this, what we do is we take a filament, we apply very high potential difference here. Okay, high potential difference. When we apply high potential difference, what will happen? This electron starts coming out, ejected outside. Okay, these are the electrons. Electrons start coming out. When the filament becomes heated up, electrons start coming out. So this type of emission is known as thermionic emission. Phenomena is thermionic emission, and the electrons are known as thermal electrons. Once again, you take a filament and heat it. Heat it means like apply high potential difference. Okay, what it becomes red hot and starts giving out the electrons. So this phenomena is known as thermionic emission, and the electrons which are coming out from the filament are known as thermal electrons. Is that clear? Is this clear? The
Yes,
first,
sir.
okay. The second one.
Yes, sir.
What the second one? What we are doing? That is about the field emission. In field emission, what we are doing is, so we are applying a potential difference. How much? A potential difference of 10 to the power of 8 volt per meter, approximately, between the two plates, like a tube light. Have you seen a tube light? A tube light, we have a two plates here, like this. Okay, one is cathode plate, one is anode plate. C for cathode, A for anode. Is cathode negative plate or positive plate?
Cathode is negative.
Cathode is a negative plate. Very good. Cathode is a negative plate. Anode is a positive plate. You are applying the, again, high potential difference here again. Between the two plates, you are applying very high potential difference. Then what happens? Then there may be, like suppose, first of all, we'll consider there is no gas in it. Why there is no gas? What will happen if I take gas in it?
The gas will get ionized.
Very good, very good. The gas will get ionized. Means these fast moving electrons can knock out the electrons which are present in the valence shells. There is a possibility that will give rise to some other thing. So that is why we don't want any gas in it, first of all. Now what happens? It is completely vacuum evacuated chamber. This is a vacuum evacuated chamber. We pulled out the air from it and we fixed the two plates in it. Now what happened? Now when you start applying high potential difference, electrons start coming from the cathode plate and go towards anode plate.
So cathode ray.
This very good, very good. This phenomena this is said to be field emission, and the electrons are known as cathode rays. Is that clear? This phenomena is known as field emission, and the electrons are known as cathode rays. Is that clear?
Yes, sir.
Okay, very good. Please copy this quickly. Then we'll go to the photoelectric emission. Just wait for some time. I'm going to explain this. Okay, this is about the Einstein's photoelectric effect. Done with this? Okay, I'll draw this here. Should I erase this part, the upper side? Yeah, this one. Okay, now the third one is photoelectric emission. Photoelectric emission. Photoelectric emission. What happens in photoelectric emission? You are taking a plate. Okay. Then when light is made to incident on this one, plate, then what happens? Electrons are ejected out. Okay, when light is incident on this plate, then electrons are ejected out. This phenomena is known as photoelectric emission. Is that clear? Once again, when light is made to incident on this play, then electrons are ejected out. This phenomena is known as photoelectric emission. This was first explained by Hertz, then Lenard's, then continued with Albert Einstein. Okay. Is it clear? This phenomena is known as photoelectric effect or emission, and the electron is known as photoelectron, and the surface is known as photosensitive surface. Once again, when light of certain frequency is made to incident on a surface, then electrons are ejected out. This phenomena is known as photoelectric emission or photoelectric effect. The electrons which are ejected out are known as photoelectrons. Okay, and the surface is known as photosensitive surface. Clear? Surface is known as photosensitive surface. Photosensitive surface. Photosensitive surface. Here I am writing here. These rays are known as cathode rays. Please do write there. These electrons are known as thermal electrons. Cathode rays. These rays are known as cathode rays. These are thermal electrons. These are photoelectrons. Photoelectrons. And the phenomena is known as photoelectric emission or photoelectric effect. Is it clear? Please do write then and there itself. No need to again write separately. And this explanation you can write in your own words. Okay. Done? Okay, shall I go ahead then? Are you done with this? Once again, see, there are three types of emission. Thermionic emission, field emission, photoelectric emission. What is thermionic emission? When you take a filament and apply very high potential difference, and the filament will become red hot and starts giving out the electrons. This phenomena is known as thermionic emission, and the electrons are known as thermal electrons. Number one. Number two, field emission. What happened here? Here we took a vacuum evacuated tube, means a tube in like a tube light. There is no gas in it, completely empty. Okay, so we pulled out the air from it or the particles. Now there are two plates fitted in it. One is C and A. C for cathode, A for anode. Cathode is a negative plate and anode is a positive plate, and we applied very high potential difference. Then what happened? Electrons started coming out from this one. So this phenomena is known as field emission, and the electrons are known as cathode rays. Now, what happens if there is a gas? What they do, I will tell you. They will take zero group elements. You know what is zero group elements?
Yes, sir. Noble gases.
Yeah, there are 4 names for it. When we like something, we start giving so many names. Example, noble gas, 8 group elements, inert gases. Yeah, zero group elements. Many names are there for them. So suppose these, why these are given that name? Now, these elements, these atoms will never participate in any reaction. They are stable, very, very stable. They don't participate in any reaction because they follow the octet rule. Now, in the suppose what we do is we can also fill it completely with that type of gas. But if you see tube light is giving which color light?
White, no?
White color light. Very good. Why only white? There are some tube lights with hue green, with hue orange, with hue some other colors also. Have you seen that? Some tube lights. Some tube
That
lights.
depends on the gas that they take.
Very good. It depends on the gas. So here in our tube light, normal tube lights, mercury vapor gas is filled. So what happens in those things? Okay, there. Suppose what happens is, suppose this is an atom. Okay, this is an atom. So when an electron gains energy, okay. So when an electron gains energy, what happens? The electron will jump to the higher energy level.
Okay.
So we are using
Eliminate
Bose model.
there it will be there for a 1 nanosecond, very, very small time, and immediately starts jumping down. It jumps down. When it is jumping down, it releases energy in the form of light. This light we are able to see. This light, the tube light, the light which is coming from the tube light is this one, not this one. This is the incident one. This is the incident radiation, or it may be energy what you are giving, potential difference. Electron will jump from the lower level to higher level. It will be there for 1 nanosecond. It will come down immediately and releasing light energy in the form of light. That light we are able to see. Suppose it depends on the atom. It is mercury vapor gas, so it is giving white color light. If it is some other gas, maybe freon, some other gas, I don't know whatever the gas is. If there is some other gas, it will give green or orange or any other color light. Okay, so that is how it works. Is that clear? Is this clear?
Sir.
So this is how the tube light or whatever it works. Okay. Now, we will go with the photoelectric effect. The first experiment is Hertz observation. Shall I start? Yes, sir.
Yes, sir.
Okay, sure. Starting with the first one. Here we have photoelectric effect. Photoelectric effect by Hertz experiment. Who is Hertz? Any idea? What is his contribution to physics?
We use his name for frequency, sir.
Yeah, very good. We used it for frequency, but he is the one who discovered microwaves. He is the one who discovered microwaves. Okay, so that is how he is popular actually. In somewhere in 1887, this man. Okay, in 1887, he found out the photoelectric emission. Okay, photoelectric emission was not discovered by Albert Einstein. Was actually discovered by Hertz. Okay,
It was only explained by Einstein.
Huh? Yeah.
It was explained by Einstein.
Experimented by Einstein. The same thing happened. No, who the J.C. Bose was the one, not only theoretical, but he found out the way how to convert electrical wave into electromagnetic wave, but not of large centimeters, small centimeters, small length. But this fellow Marconi was little smart, so he took that idea and he did the same experiment on the across the Atlantic Ocean for around 5 meters or something, or 5 kilometers, and he fitted that and he found out that radio. He invented the radio, for which he got the Nobel Prize. So this happens, you know. Okay, so that is why we make the patents. And whenever we do some research, immediately we make our own patents so that nobody should steal our idea. In those days, this concept was not there. Now, so Hertz experiment, what happened is he was doing the experiment of electromagnetic waves. Okay, well, he was the one production of he was doing the experiment on production of electromagnetic waves. He was doing experiment on production of electromagnetic waves. Okay. Now, by the means of the experiment was spark discharge experiment. Spark discharge experiment. Okay, production of electromagnetic waves using spark discharge experiment. Now, when he applied high potential difference, high voltage across the detector loop. Okay, so what happened is, like suppose he took a some type of thing like this. Okay, here this is a emitter, E for emitter and C for collector. He took like that. Okay, so he took E for emitter. So what happened is this was like ultraviolet light was incident on this ultraviolet light was incident. It was made to incident on the emitter. Then what happened? Electrons started coming out. Okay, and they were collected by the collector. So, and what happened exactly? The electron got the electrons which are on the surface of the plate. They got enough energy, and they started moving out. Okay, electrons, when ultraviolet rays were made to incident on the plate, then what happened? Well, ultraviolet light was made to incident on the plate. Okay, what happened? The atoms, the electrons which are in the outermost level, they got enough energy, and then the electrons started coming out. This phenomena he named it as a photoelectric emission. Is it clear? This actually he found out while doing the experiment. Actually, he did not do it intentionally, but many discoveries are there which were found, which happened in that way. Okay, please copy this. We'll go to the next one.
Yes.
What we say, incident or accident?
Accident, sir.
Accidentally, yeah,
Oh.
very good. Accidentally, we found out many things. The same Faraday's, when I was explaining Faraday's experiment also, that also happened due to it. That is all that accidentally, not by doing the experiment. Okay, so I'm going with the next one, Hall's and Lennard's observation. What did they say? So the second, the second one is Hall's. Here, Hall's and Lennard's observation. Hall's and Lennard's observation. Okay, so okay, so the same experiment, they also did the same experiment. So what happened is when this is the plate, cathode plate. Now they, instead of writing emitter plate, they wrote as cathode plate, and this is an anode plate. Okay, this is emitter. This is the emitter plate, and this is collector plate. And what happened? They apply potential difference across it. And what they did, when light was made to incident on this one, then electrons started coming out. The same whatever the Hertz has done. Now when they stopped it, when the ultraviolet rays were made to stop, immediately the electrons coming out here, they connected one ammeter also. They connected one milliammeter or microammeter, very small. What is the range of milliammeter? What is the range? Okay.
It can measure like 1 to 10, 1 to 20 milliamperes, maximum till 20. It measures in milliamps, that's it.
Yeah, milli means 10 to the power of how much? 10 to the
Minus
power of
3.
-3. And micro means 10 to the power of
-6.
very good, -6. Very small amount of current to detect the flow of current. Okay. So when light was made to incident, when ultraviolet rays were made to incident on the emitter plate or cathode, then electrons started coming out. This phenomena already we know it is a photoelectric emission, and the electrons are known as photoelectrons. And collector was collecting the electrons, and they connected a milliammeter and microammeter to see the flow of electrons. They proved it experimentally. Or not only that one, they changed the surface of this also. What they took different elements like zinc plate or some other thing. Okay, they took zinc plates or some other elements. Okay, they took some other elements and they did the experiment like this. Okay, on this plate they took zinc, they took sodium, they took some other elements and they did the experiment. And that is how they carried out. They found out the difference between the different elements. Got it? So which will give more electrons, which will give less electrons. Then they varied the voltage, like different parameters. One parameter is the element, the surface what they have selected, zinc, sodium, something. Second was light. Third was the potential difference. These three parameters they varied and they studied about it. That is what Hall's and Lennard observation is. Is that clear? Is it clear?
Yes, sir.
All of it.
Yes, sir.
So once again, here there are three parameters. What are they? Number one, the light. They changed the color of the light, ultraviolet rays. They changed it. Okay, varied. The second one, they changed the plate. Third one, they changed the potential difference. These three things they varied and they studied about this experiment. So that is what is Halbach and Lennard's observation. Clear? Now, I am going to experimental study of photoelectric effect. This one. At last it came now. Experimental study of photoelectric effect. Just give me a minute. Okay, so shall I go with the next concept? Experimental study of photoelectric effect. Now, experimental study of photoelectric effect. Experimental study of photoelectric effect. Okay, so this is the source. This is the source, and same this is a cathode plate. This is the anode plate. Now, this surface is known as photosensitive surface.